We see you fine.
Okay, perfect. Thank you very much for the introduction, Paul. My name is Christina Brantl. I'm with RWTH Aachen University, and I'm going to present today on harmonization of grid code requirements for HVDC systems. So I'm going to start just with a short overview on existing grid codes for HVDC systems, and then go in more detail on HVDC system design and DC grid code requirements. So the starting point in promotion was the ENSO-E network code. It was the first published network code on requirements for grid connection of HVDC systems and direct current connected power park modules. And it mainly specifies the converter behavior at the AC point of connection, because the HVDC system was the new part integrated into the existing AC grids. So specifications in this grid code were, for example, frequency and active power related ranges and control modes, AC voltage ranges, reactive power ranges and control modes, AC fault right through, and the short circuit contribution. There were no specific statements on the DC side. And in general, the ENSO-E grid code as the first basis trying to tie together the different national GSOs provides a very broad range of possible specifications. And then we had a further look at the refinements that were then done in the national implementations. And what we saw there, so on the right-hand side is the overview of the implementation status. I accessed it yesterday, but I think it's not completely correct. So in some cases, the national implementations are already further approved or binding or submitted for approval than shown here. But what we had a look at is the technical specifications in those different national specifications to see how much is the current status aligned. Maybe there's possibility for further alignment if needed, if possible. So what we saw that some aspects are really specified in a very similar fashion. So one part would be, for example, the AC fault right through levels required at the AC connection points, and then a requirement to support the AC systems with reactive power support. But we also saw there's quite a divergence on the detail of the specifications, which might be due to the number of HVDC systems, for example, connected. Some aspects are specified, for example, with different timings. One that I would like to point out here is, for example, fast fault current contribution. So the transient behavior or the behavior under faults, there are quite different ranges stating from there has to be a fast or a fault current contribution with no timing indicated, or timings in the range of 50 to 90 milliseconds. So that leaves quite a lot of room for converter design here. Some countries impose requirements. For example, inertia provision is required in some countries and not in others. And what we also saw is that the specifications or the numbers that are then given sometimes take into account possible converter capabilities, so the speed, for example, of power flow reversal, and some rather specify this from the perspective of the connected AC system requirements. Of course, this takes into account that the different countries have different requirements, different numbers of HVDC systems, different power plant parks. However, if we now move from the AC side and want to create a DC system here, for example, in the North Sea, what promotion mainly focused on, then we really to be able to interconnect the different DC connections. For example, if we have a wind farm here and want to connect it to Great Britain and the continental European grid, then it would be very beneficial to have an aligned and harmonized set of requirements on the DC side. So let's now have a closer look at HVDC system design and DC grid code requirements. Well, existing systems, as you might know, mainly point-to-point, some multi-terminal systems, but mostly one vendor. Now, if we want to move from those two systems and want to interconnect them in a certain way, we have to think about different system design aspects. So one would be the DC voltage level, but also the DC system configuration. And by configuration, I mean here, is it, for example, a bipolar system or symmetric monopolar systems? Both configurations are used in existing systems, but combining these would be rather difficult. Then we have to think about what's the operational strategy. What do we want to use the offshore grid for? There might also, so is it wind farm export? Is it interconnector capacity? And one very important part is then that is often discussed is interoperability. And I think this will also be presented again in the ENSO-E presentation. So if those converters come from different manufacturers, for example, or are different ages, different control modes even, how do they interact and how can we ensure that it's a stable system operation? Another important part, if we connect them on the DC side, is how do we handle DC side faults and contingencies? What Paul showed before, that was a large part of promotion. And what you can say about this is that we then have to define how do we want to define reliability and availability criteria for a DC grid. This is not yet defined. And also, what is the impact of faults and fault clearing strategies? There's quite a broad range of possible fault clearing strategies, and not one is better than the other. So there is not a standard yet for the DC fault clearing. The next part is that this offshore grid for wind export also have the offshore wind farm systems in here. And so far, the existing definitions mainly try to, you have the main definitions here at the connection point offshore. And then, for example, you try if you have an AC fault in the AC system. For the offshore systems, you apply a chopper to have the wind farm not basically see any electrical response to this. So the wind farm doesn't really notice that there was a fault in the AC system. But maybe we want to use the control capabilities of the offshore wind farms for DC fault right through, for AC fault right through. Maybe we also want to use them for support of the AC systems using, for example, grid forming controls and black start. So there's a lot of options that we could use this wind farm capabilities and converter control capabilities in the wind farms further. The next part is if we go to even larger DC systems, we have to take into account the AC system dynamics. So what does the DC system need to take into account? For example, respect the different frequency reserves, how is the AC fault right through, and what kind of auxiliary services need to be provided by the DC grid in total if these systems get larger. So on this basis, if we now want to design an HVDC grid code, the prerequisites for a grid code are that it's discrimination-free, that there is interoperability that applies to different components that we want to use in the system, but also multi-vendor. This should be plug and play. It would be nice to just be able to change a component like we are able to change, for example, an AC circuit breaker in the AC system. But at the same time, it should not inhibit technological development. So within DC systems, there's still quite a lot of research ongoing. There's a very fast development of the technology and also the knowledge on these systems. So the grid codes should give functional requirements, most likely at the border point, so at the point of connection for the converters. And we have to find a balance for different solutions and system requirements. This is very challenging. So when within the project we started discussing what could be possible parts, we ran into several challenges. And therefore, I'd like to point out what is the basis for the AC transmission system grid codes. So what was it? Is it possible right now to specify the system as it is right now for the AC systems? We have given system voltages, a given grounding strategy. We have a known passive behavior of generators, for example, on the faults. We have standardized fault clearing sequences and components. So the standardization is already a lot further, and we understand that system better. If we now look at DC systems, planned and existing systems, there's a range of different DC system voltages. There are different configurations possible. So for example, up on the right, the symmetric monopole, which doesn't have a grounding on the DC side, or the bipole with metallic return, which does have a grounding on the DC side, leading to different behaviors under fault. And it would be very difficult to just have a grid code that allows plug and play of, for example, these two system configurations. And then we have the fact that the converter behavior depends on the system or the converter design and the controls that are implemented. That leads to different control modes that could be active. For example, the converter connected to wind farm is in a different control mode than one connected to the onshore grid, but also that different vendors implement the different controls differently, and these are protected by IP rights. So these controls can interact, and there are several approaches how to analyze these interactions. One would be, for example, the multi-frequency analysis, so an impedance analysis that we have another presentation on. And these are then building blocks to further understand the system and the control and the interactions. Another challenge that we faced was that with all those different possible fault clearing strategies, if we want to try to design a DC fault right through curve similar to an AC fault right through curve, that depends a lot on how we design the fault clearing strategy. The left curve here would be, for example, DC fault right through strategy that we could define for a system where we have a certain DC circuit breaker type with a certain timing. And then we could specify, for example, this DC fault right through curve in a generic fashion at the converter terminal. However, if we use a fault clearing strategy based on converters that have fault control options, then the converter actually has to actively control the DC systems during this period, has to sustain a certain zero voltage for a certain time, and then has to recover the system. So the requirements on the converter are very different from the ones here. And this makes it very difficult to define a grid code which is applicable to all different possible DC system configurations, topologies, and converter types. So if we want to get closer to this, so we're kind of starting here with a very broad range of possible system designs and ongoing technological development. But what we want to have at a certain point is a grid code that allows plug-and-play integration of the new converters and also other components. So one key part is understanding of the system behavior and implication of design choices, and Promotion has done a broad range of studies on all certain aspects and has pointed out what are requirements, for example, on fault clearing strategies, how do the different systems act, has demonstrated different control choices. And based on this, at some point, there will be need to at least have a decision for certain system designs. And if it's just, for example, starting with different system voltages, to be able to later connect the different systems. Then also a closer specification of required system behavior at the connection points. At the moment, there is still quite a gap between those two. And of course, one part is making this gap smaller by further specifications, better understanding, or more choices for the systems. But right now we have to bridge this somehow. And for this, there are a lot of proposed interaction studies, for example, using replica systems, hardware-in-the-loop analysis, impedance models, EMT models, or other models. And within this part, Promotion has also done quite a lot of work to be able to specify those systems and to analyze those systems. So while we still have this gap, bridge this. Thank you very much for your attention.
Thank you very much, Christina. I will encourage you to use the chat to raise questions. I have not seen any questions for Christina's presentation at this point. There is a new one now. Okay, Philip Tønderhof, thank you. He has a question. Who would you say is responsible to close this gap?
That's a very, challenging question as well. So one role might be for TSO to decide on common standards for example, the North Sea region. So NSOE might be a possible group that could decide on, okay, we're going to focus on these and just set this as a first step. And then for the other parts, the one very difficult topic is the converter control, for example. So right now, it's the converter is completely designed by the manufacturers. They will be integrated into the system with different interaction studies. I know there are other approaches where, for example, the upper level controls might be in the hand of the TSOs at some point, and the lower level controls are kept within the IP domain of the manufacturers. So there might be a shift on where the knowledge is on the system and how to control and design the system. So to be really able to specify requirements on that connection point, somebody has to take over the responsibility to design the DC side grid and has to say, okay, we're going to design it this way, and this way we can also then specify the requirements at the connection point.
Yeah, okay. Then we have questions are coming in now. We have one from Tobias Gilhaus from DMDGL. He is asking which time horizon do you think will be for plug and play HVDC systems?
I'm not sure.
That's also a difficult question also, but
yeah, I think
but a very relevant question, I would say, but also a difficult one to answer.
Yeah, I think what Promotion also proposed is that as a next step, we really have some systems where we have the DC interconnection, testing interoperability in short-term projects, for example, between different vendors or between different systems. That would be an important step, but I can't, and that should happen soon, but I can't comment on which time horizon will be there in the end. I think NSOE has a plan for this, but I can't comment.
Maybe a general comment also from my side is that I mean we also have gaps in the AC system, and they are arising from the changes that are in the system. But I think this is probably going to be a process also. Then we have Mian Wang. Do you think plug and play is realistic for such complex a system as an HVDC grid? So do you actually think it's possible?
Personally, I don't think we can completely close the gap. There will be some need for interaction studies because it's such a complex system and we don't have an inherent behavior, and we might have changes in control modes or developments in control modes. But I think we still need to make the gap a little smaller. So plug and play will probably not be possible for everything, but at least get closer to it.
Yes. Okay, then I think we should go to the